Thank you. Just this. Okay. Thank you so much, everyone, for coming. Different settings, but I see we have still a quite good crowd. Let me remind people online, if there is anybody, that if you don't want to appear in the video, this is a good time to turn off your camera. So we're very glad to have today two speakers. They are both from remote. Let me introduce the first one, Ping Zhou. She's an associate professor at Nanjing University. She got her PhD at Nanjing University in 2014 and worked as a Veni postdoctoral fellow at the Anton Pannekoek Institute in Amsterdam, University of Amsterdam, during the period 2016-2020. In 2021, she joined the faculty at the School of Astronomy and Space Science at Nanjing University again. Her research focuses on supernova remnants, interstellar medium, isolated neutron stars, and she's also interested in historical records of transient sources. She's participated at IXP Supernova Remnant Topical Working Group, and she joined the science groups of LASO, the Large High-Altitude Ray Shower Observatory in China, and also future missions like EXP, the Enhanced X-ray Timing Polarimetry, and the HUBS, the Hot Universe Baryon Surveyor. And today she's going to talk to us about the imaging the X-ray polarimetry of supernova remnants. And with this, the floor is yours.
Thank you very much for the introduction. Hi, everyone. First of all, I would like to thank Beijing and the organizing group of the head seminars for the invitation. I'm very glad to have the opportunity to discuss with you and share with you our recent studies about supernova remnants using imaging X-ray polarization measurements. The works in this talk are done by the people in the supernova remnant topic working group in XP and by also other members in XP science team. We also have some external collaborators, including Estela Reynoso and David Moffitt. There are two main questions we want to answer using the polarization measurements of supernova remnants. The first one is how are magnetic fields distributed in these remnants, and how are the strong magnetic fields generated in supernova remnants? The two questions are very important for our understanding of the origin and propagation of very high energy cosmic rays. Cosmic rays are high energy particles traveling in the space with the speed of the light. In the 1930s, Bud and Saikia has speculated that cosmic rays can be generated from supernovae. This speculation is brilliant, but it was not proved from observation until 1950s. The radio observations have revealed the supernova remnants can generate synchrotron emission. This emission is non-thermal emission radiated from high-energy electrons rotating in magnetic fields. Another group of evidence comes from the X-ray and gamma ray observations. This picture on the right-hand side shows the GeV gamma ray all-sky survey made by Fermi Large Telescope. On the galactic plane, you can see some bright extended sources. They are supernova remnants. From the multi-wavelength observations, we have very good evidence that supernova remnants can indeed accelerate cosmic rays, including cosmic ray particle, cosmic ray protons. But there is still a very crucial question unsolved. Are supernova remnants the primary source of galactic cosmic rays? If you want to answer yes, there are two basic requirements need to be satisfied. The first one is the energy. We must answer whether a supernova remnant can transfer sufficient energy to cosmic ray energy. Although we do not have a clear answer to this requirement, but people think that if supernova remnant can transfer 10% of its energy, genetic energy, then the energy budget problem can be solved. The second problem, the maximal energy problem, is the more severe problem. This requires that at least some of the supernova remnants must accelerate cosmic rays to 3 × 10⁻⁵ eV. This energy is at a break point of the cosmic ray spectrum, as shown in the left figure. Its energy is also called the knee of the cosmic ray spectrum. Below the knee, the cosmic ray particles are believed to be accelerated in our galaxy. So regarding the maximum energy, we must consider magnetic fields. The strong magnetic fields can trap and mirror the cosmic rays near the shock in order to accelerate the cosmic rays quickly to very high energy. In this equation, Emax is the maximum energy of cosmic ray accelerated in the early phase of the supernova remnant. You can see that Emax highly depends on the magnetic field B, but weakly depends on the supernova properties, because you can see the index here is small. Briefly, we can just think that parameters in this box is similar to 1. So the magnetic fields becomes the most important factor here. In the diffuse ISM, the magnetic field strength is around 1 micron Gauss. If we put this value here, you see the Emax is around 50 TeV. But we want the energy to reach 3 × 10⁻⁵ eV. In this case, we need the magnetic field to be amplified by 100 times. A good news is that the magnetic field amplification in young supernova remnants has been an observational fact. Here you see 4 young supernova remnants with age less than 1,000 years. And at boundary, you can see a thin filaments produced by the synchrotron. They are synchrotron, non-thermal synchrotron emission. And these filaments widths tell us about the magnetic fields. The thinner the filaments are, the stronger the magnetic fields. For example, for case A, we will obtain the magnetic field of around 0.1 milligauss. This is around 100 times larger than that in ambient diffuse interstellar medium. Now we already have this observational evidence of magnetic field amplification, but there is a lot of uncertainty in the theoretical interpretation. We still not clearly know which mechanism causes the amplification. There are a lot of theoretical studies. Here I mentioned 2 popular scenarios. The first scenario is about the cosmic ray induced instability. It can create the magnetic turbulence and amplify the magnetic fields. In this figure, you see the cosmic ray is streaming in the pre-shock region and into the uniform magnetic fields. Magnetic fields lines are indicated using the solid lines. And very quickly, the cosmic ray streaming energy can be transferred to perturb the magnetic field, and you see these curvy structures for the magnetic fields. This is one mechanism. The second mechanism is called turbulent dynamo. This requires that the supernova remnant is expanding into the non-uniform medium, and there is a lot of turbulence in the there is turbulence energy in the ambient medium. And this simulation shows such a case. And you can see in the post-shock region, there is a lot of structures like instability and finger-like structures. The upper panel shows the magnetic fields, and the post-shock region. In the post-shock region, magnetic field can be enhanced to tens times of the ambient magnetic fields. The requirement for this mechanism to work is the density fluctuation in the ambient medium. And a prediction of this scenario is the radial distribution of the magnetic fields. You can see the magnetic field, there is a component parallel to the expansion direction. Now we have these two different mechanisms. We still need observations to tell us what is going on. We need observations to really tell us what is the magnetic turbulence is and what is the magnetic orientation, and efficient ways to do X-ray polarization measurement, because the measurement can tell us at least two information. One is polarization degree, and the second is polarization angle. The polarization degree can tell us about the turbulence level or whether the turbulence is isotropic or not. The polarization angle can tell us about the magnetic orientation, because the polarization direction is perpendicular to the magnetic orientation. Some people may say that there are already a lot of radio polarization measurement of supernova remnant. Why do you still need X-ray polarization imaging observation? The X-ray emission and radio emission are generated by electrons with totally different energies. The X-ray emission is generated by very high energy electrons, which lose their energy very quickly. So this the X-ray polarization can probe the magnetic field close to the shock front, where the very high energy particles are freshly accelerated. This is the information we want. We use the observations taken by XP. XP is the first imaging X-ray polarimetric telescope. It provides an angular resolution better than 30 arc-second and a field of view of 13 arc-minute. So this allows us to study extended sources such as supernova remnants. Now, XP have observed 5 supernova remnants. In this talk, I will focus on the first 3, Cassiopeia, Tycho, and SN1006. As the second targets, we have RCW86, RxJ1713, and Vela Junior. We have already found some new and surprising results for the second year supernova targets, but this will be mentioned by future talks by someone else. Okay, Cassiopeia is the first science target of XP. Maybe many of you know Cas-A is a very beautiful supernova remnant, very bright in the X-ray band. Now we have the first view of the distribution of X-ray polarization for this remnant. Here, it shows the polarization degree distribution, and the contours shows the non-thermal X-ray emission level. Only the pixels larger over 2 sigma significance are shown. Here you can see 2 vectors. They are polarization angles, telling us the magnetic fields the magnetic fields aligns the shock normal direction. So here you can see that the significance is not very large, but we want to use all these signals. So we did some technical things. We assume that at all the regions, magnetic fields is readily distributed. So we can obtain the average polarization of the whole supernova remnant, which is only 2.5%, and the polarization degree at the boundary is higher. This can also be indicated using the distribution of these pixels. The polarization degree at the rim is about 5%. compared to very beautiful Chandra Cas-A image, the polarization image of Cas-A is not so pretty, but we still think this is a very nice result because it tells us the polarized X-ray light is really light is really faint. This is because the polarization degree is low and the magnetic field is highly turbulent. This is also very interesting. Okay, this is the first target, and our second target is Tycho supernova remnants. Here is also the polarization degree distribution, and the vectors shows the polarization angle. Then it means that the magnetic field is still parallel to the shock direction. The magnetic field direction is perpendicular to the polarization direction. Okay, and so for this supernova remnant, we obtained the average polarization degree is 9%. But the polarization degree is not uniform across the remnant. In the northwest, we found a higher polarization degree, which is around 20%. So the overall magnetic field distribution is radial. This is very similar to what we found for Cassiopeia. Our third target is asymptone 6. Because this is a very large supernova remnant, the field of view of the XP is much smaller, so we only cover the northeastern region. The middle picture shows the polarized emission distribution, which is correlated with the X-ray brightness. The picture on the right shows the polarization degree distribution. The average polarization degree is around 20%. And the vectors here shows the magnetic field distribution. So it's clear that magnetic field is parallel to the shock direction. So the magnetic field is still radial. So this is the common property for all of the three young supernova remnants with ages less than 1,000 years. This is interesting because it's very different from that found for old supernova remnants. The picture on the left-hand side is old remnants called CTA1. The observation is taken from the radio band, and the black vector shows the magnetic field direction. So it is tangential to the shell. This is opposite to what we found for young supernova remnants. The magnetic fields are radially distributed. For the old remnant, we think the magnetic field orientation is due to a compression of the magnetic field in the interstellar gas. This means that for the two groups of supernova remnants, magnetic amplification mechanisms are different. Okay, I will speed up. So how do we explain the magnetic field of these remnants? We have considered three possible scenarios. The first one is the MHD effect. As I mentioned earlier, this effect tends to create radial magnetic fields, but it requires non-uniform medium. This requirement can be met for Cas-A and Tycho, but not for asymptone 6. The second possible reason is selection effect. It is think that the cosmic ray acceleration can be more efficiently when the shock is parallel to the magnetic fields. In this case, as a result, the X-ray emission can be enhanced when the shock is parallel to the magnetic field, but the X-ray emission can be suppressed in the tangential, in the perpendicular magnetic fields. Here is a simulation shows the selection effect. Even if the magnetic fields is totally random, we tend to find find radially distributed magnetic field according to the polarization measurements. The third possible reason is that the pre-existing field direction is kept. Now we think that maybe for different supernova remnants, different mechanisms are working. At least we can exclude MHD turbulence for SN1006. Another interesting result we get for these three remnants is the low polarization degree, indicating that the magnetic field is highly turbulent. And another information is the turbulence scales have not been resolved by the XP observation, because if we can resolve the turbulence scales, we can find ordered magnetic field and high polarization degree, right? And with this result, we also want to discuss these two magnetic turbulence scenario mentioned earlier. The first thing is the cosmic ray induced instability. We obtained that length scale according to the Bell's equation, as mentioned here. The turbulence scale induced by this mechanism is between 10 to the 16 to 10 to the 17 centimeter. So this value is smaller than the spatial resolution with XP and the X-ray structure. So that means that this length scale cannot be resolved. This can explain the low polarization degree. This is good. And we also consider the second scenario, turbulent dynamo. As mentioned earlier, it does not work in SN1006, but it should work in Cas-A and Tycho. Because it does not explain SN1006, and SN1006 has a low polarization degree. It provides us a hint that cosmic ray induced instability set the magnetic turbulence in SN1006. Finally, an interesting thing, the interesting thing is that we found a range of polarization degree in different supernova remnants. That means that turbulence levels are very different. So how to explain this? I think we still need more studies, but we think that the environment could be a reason, because SN1006 is in a uniform medium and Cas-A is in a very highly clumpy medium, and Tycho is around the middle. So the density fluctuation is increasing from the right to the left. And so the turbulence dynamo should working at a more significant level from the right to the left. And this caused the highly turbulent magnetic field in Cassiopeia. We think this could be one explanation of the different polarization degree in these three supernova remnants. If this scenario is correct, this would suggest that magnetic turbulence and thus cosmic ray acceleration is environment dependent. Okay, so finally, here is a summary. I think I just put it here to save time, and now I'm happy to take questions. Thank you.
Okay, do we have any questions from here? Did you hear the question?
Oh, sorry, I cannot hear. The voice is very small.
Yeah, I repeat the question. Do you have any data about the crab?
Oh, there is XP observation of the Crab Nebula, and the polarization degree is around 20%, but the maximum polarization degree is much higher. I think it's over 50%. That is large. So it gives a hint that the magnetic turbulence level is different between the supernova and Payaswini nebula, and possible the cosmic ray acceleration mechanisms is a little bit different.
Okay. Any more question? I might have a question. So you pointed out that the turbulence length scale is much shorter than the XP resolution, spatial resolution. So
yes.
Yeah, so you alluded to this. So is it possible that the large scale magnetic field we are sampling with the XP has nothing to do with the magnetic field, which is responsible for the particle acceleration, which has to be turbulent in order to maintain particles close to the shock and further acceleration. Is it possible that the real magnetic field, which we are interested in, that we want to connect with cosmic rays, lives on much smaller length scales, which you are showing here? The ones from the density fluctuation mechanism are about the same. So they are about 1% of parsec. So is it possible?
So here is I only, to save time, I only mention the spatial resolution of XP, but the non-thermal X-ray structures vary from one source to another. We think that XP resolution is quite large, and we need to consider the filament width as an upper limit. So for the we think that turbulence scale should be smaller than the filament width and XP resolution.
Right. Okay. All right. Thanks.
Okay.
I don't see any question online. No? Okay. So any more questions from here? I cannot see. So let's thank you again.
Okay. Thank you very much.
The second speaker. Payaswini, can you try to share the screen?
Yes, give me a second.
Okay. Yeah, that should be fine. Yeah, thanks.
Can
okay,
you see it now?
Yeah,
okay.
Should be fine. Yeah, we just see the toolbar at the top.
Yeah.
Yeah, no, it's well readable. Okay, so the so the second speaker is Payaswini Saikia. I hope I pronounced correctly. So she's currently postdoctoral associate at New York University, Abu Dhabi, and she's interested in phenomena of accretion and ejection in stellar mass black holes. She's currently using multi-wavelength observations, especially optical and infrared wavelengths, to investigate the accretion processes in the disk, relativistic nature of jets, and disk jet coupling in X-ray binaries during outburst. She earned her PhD at Radboud University down in the Netherlands, looking at theoretical predictions and the observational verifications to establish unification of stellar mass and supermassive black holes, and used the black hole scaling relations along with state-of-art radio observations in the local universe to shed light on the different properties of relativistic jets in AGN. And she let us know also that she is actively looking for a postdoc position after this. Thank you so much. The title of her talk is Swift J1910.20546, optical monitoring of a black hole X-ray binary. Thank you. The floor is yours.
Thank you. Good afternoon, everyone. I'm Payaswini Saikia, postdoctoral associate from New York University, Abu Dhabi. I was actually in Boston earlier this month for a collaboration visit at MIT, and it would have been great to give this talk in person while I was there, but I could not materialize it this time. Nevertheless, I'm happy to have this opportunity today to present in front of you some interesting science we have recently done with our long-term optical monitoring of a black hole X-ray binary, Swift J1910, which resulted in 2 recent papers that I'm citing in the slide for the ones who are interested in a detailed read later. Okay, Swift J1910, the source that I'm focusing today, is a low mass black hole X-ray binary, which is basically a stellar mass black hole that is accreting matter from a low mass companion star. These X-ray binaries spend most of their time in quiescence, where their accretion is very, very minimal and their luminosity is low, making it very, very hard for us to detect them observationally. But occasionally, they go into a state called as an outburst, when their brightness in every wavelength increases by several orders of magnitude. Now, how these outbursts happen is still debated. And the most widely accepted theory right now that we have is the disk instability model, a model that was proposed mainly for understanding white dwarfs, not black holes or neutron stars, which says that in quiescence, the accretion disk slowly fills up with the matter that it is accreting from the companion star. And as it slowly fills up, the temperature rises until at some radius, the hydrogen gets ionized, triggering the outburst and making the brightness go much, much higher in all the wavelengths. Now, although we do not completely understand, we know that these outbursts are really important, especially for observational astronomers, because although there are probably thousands of stellar mass black holes, a lot of X-ray binaries in our own galaxy, they are very hard to detect unless they are in outburst. Swift J1910, the source that I'm talking about today, was also discovered when it went into an outburst by Swift and Maxey in 2012. Here I show you the X-ray light curve of the 2012 outburst of the source. It was mostly studied in the X-rays during the 2012 outburst, and there are some loosely constrained values of the system parameters, like the mass of the black hole, the orbital period, distance, inclination, etc. Now, all of these are not properly known, but we know that the mass is more than 3 solar mass. We know that the orbital period should be something more than 2 hours, and it is expected to be at a distance which is higher than 1.7 kiloparsec. This is the 2012 outburst of Swift J1910. The two top plots that I show here are the X-ray light curves with Maxey and Swift at 2 to 20 keV range and 2 to 10 keV range. And in the bottom panel is the optical evolution of the source in different wave bands with the LCO telescopes. With our LCO monitoring, we find that during the outburst, the optical emission that is coming from the system mainly originates at the outer part of the accretion disk. Here I show you the optical UV spectrum of the source with different frequencies plotted in the x-axis and quasi-simultaneous flux densities plotted in the y-axis. Now, the shapes that you see here of these SEDs, these are fairly typical of low-mass X-ray binaries, where the optical UV emission is dominated by the Rayleigh-Jeans part of a blackbody spectrum. But what is not so typical is that we find a dip in the intensity of the source around 90 days into the 2012 outburst, and what implication this dip has for the hardness intensity diagram of the source. Okay, so the dip that I'm talking about was also detected in X-rays, infrared, and UV wavelengths. We find that the optical dip happens first, followed by the UV dip, which happened almost 3 days after. And then the dip is observed in the X-rays, after which we also see a dip in the X-ray hardness. So we know that because the dip is not happening at the same time in all wavelengths, so it is not something which is coming from the outside. We think that this observed delay in the occurrence of the dip at different wavelengths can be attributed to some kind of a radial inflow of mass instability from the outer edge of the accretion disk coming towards the inner region as the accreting matter propagates from the outer part of the accretion disk near to the black hole. And interestingly, this dip creates an interesting feature in the hardness intensity diagram of the source. So for the people who are not working on X-ray binaries and accretion, generally, when we plot the spectral hardness of the X-ray binary versus the X-ray brightness, most black hole X-ray binaries typically follow a Q-shaped anti-clockwise evolutionary track. The source basically moves from here, gets harder, the brightness increases, the spectra then softens, and the source gets fainter and returns back to the initial stage. Now, for 1910, by the time we Swift started observing the source, it was already in the soft state. But instead of this smooth transition that we see here from the soft to the hard state, what we see is that they have some kind of peculiar loops in this source. So basically, it starts from here at the top, the red data points, and starts to get fainter. But just after the dip happens, the source starts to soften again. and starts to get brighter. And interestingly, the luminosity when the hard to soft transition occurs is much lower than the luminosity when the soft to hard transition occurs, thus forming a clockwise loop, which is highly unusual in black hole X-ray binaries. We searched through the literature, and there was previously observed, like this kind of a behavior was previously observed only in one outburst of a black hole X-ray binary till now, and there is no explanation of why this happens. But as this transition happens just after the dip, we think that there should be a link between the matter propagating through the accretion disk and the spectral state change that we are observing. In fact, this loop that I'm talking about is best evident when we are taking the X-ray hardness ratio of 1.5 to 10 keV by 0.6 to 1.5 keV, where the X-ray range has significant contribution coming from the accretion disk. If we go to a much harder ratio, like 15 to 50 keV by 2 to 20 keV, the kind of X-ray luminosity where we do not expect a lot of contribution coming from the disk, we see that this loop gets diminished. So we think that this is probably caused by the accretion disk, and this is highly unusual and interesting. But this is from 2012, long ago. The source stayed quiet after 2012 until it created a buzz in the X-ray binary community last year, when it started another outburst in February 2022. So what was the source doing in the 10 years of time between 2012 and 2022? This brings me to the second part of my talk. So currently, the easiest and probably the most inexpensive way to monitor X-ray binaries in low accretion rate during quiescence is with optical telescopes. Because X-ray telescopes that we have, which are doing the all the monitoring, the sensitivity of them are not good enough to catch these X-ray binaries during quiescence. Our group has been monitoring around 40 to 50 low mass X-ray binaries at optical wavelengths with the LCOGT, which is the largest optical robotic network of almost 23 telescopes in 7 different sites across the world. So if we cannot observe a source during when it is day, for example, in North America or South America, then we can observe them with our telescopes in Australia. And with this monitoring, we have been able to do some really cool and interesting science. I use this slide as a quick advertisement of the kind of science we can achieve with these observations. For example, we can detect and alert the community about new outbursts or reflares happening in these systems, like we did for 4U1543, a black hole system which has just gone through the brightest optical outburst we have ever seen for this source. We can use simultaneous multi-wavelength data to constrain the distance to X-ray binaries, like we did, for example, for GRS 1716 last year, one of the black hole X-ray binaries. And we can study long-term behavior of sources in quiescence to see if there is any gradual long-term rise in the optical emission as predicted by the disk instability model, like we did for the neutron star X-ray binary SENX4, which was also published sometime last year. And it's a really interesting paper because this also shows a really important observational evidence for the disk instability model, and shows how gradually, as the disk starts to fill up with matter, the optical luminosity increases before the outburst happens. Okay, back to 1910 for now. So what did our long-term optical monitoring show? Here I show you the complete optical light curve of SWIFT J1910 from 2012 to 2022. And I want to bring your attention to these 2 very exciting periods of activities that happened in 2013 and 2014. Those were previously undocumented because X-ray telescopes did not have the sensitivity to detect this. And optical monitoring data, although we have been having this for a really long time, it's just now that we have started using all the observations and trying to find out what kind of things we have in the chaos of data that we have gathered in the last few years. So After this 2013 and 2014, these two periods of activities, we see very high amplitude, strong and repeated optical flaring in 2013. And in 2014, we see a faint but double-peaked mini outburst. The evolution of the optical color during these activities follow a bluer when brighter kind of a behavior. Now, normally, after a source has reached quiescence, such strong and repeated reflares are very, very rare. I list here all the systems that we know till now, where reflares are observed within a year of the end of an outburst. And as you can see, such high number of outbursts, such high number of reflares are rarely seen in such kind of low mass extrabinaries, which makes sense because generally the disk instability model that I said is used to tell us what triggers an outburst predicts that accretion disk should be depleted from matter at the end of an outburst, and hence cannot well explain these kind of rebrightening events which need a large amount of matter to be left in the accretion disk after an outburst. But recently, there have been some newer studies which can explain reflares using the disk instability model, provided there are some kind of specifications, like there is a hot inner disk present at the end of an outburst, especially in short period systems like J19, where the outer accretion disk is hot enough to sustain some kind of heating and cooling fronts in the accretion disk. So in order to see if this is what we are observing in our source, we try to look for the color magnitude diagram. This is one of my last slides of the talk and one of my favorite slides too. So I want to bring your attention to this. So here, basically, I show you the optical magnitude in the y-axis and the color of the source, which is basically V optical magnitude minus I optical magnitude as the outbursts progress. The red, orange, and the pink points, these are during the outburst. And I want you to focus mostly on the green and the blue points, which represent the two rebrightening epochs. We find that both the 2013 reflares shown in green squares here and the 2014 mini outburst shown in these blue diamonds closely follow the model of a single temperature black body, which was really interesting because the optical colors that we see here are consistent with a black body which is heating and cooling between something like 5,000 Kelvin to around 10,000 Kelvin, which is the temperature that is needed in the disk for the hydrogen to get ionized. So this is one of our first observations to show that these reflares are probably being caused by repetitive heating and cooling waves traveling through the accretion disk. And as the temperature reaches the temperature needed for the hydrogen to get ionized, we see kind of a start of an outburst. But because there is not enough matter left in the disk, so it cannot sustain a complete outburst, and then it just drops back. And we see this the waves to repetitively travel through the accretion disk. This was really interesting for us because there are very few sources for which we see such kind of reflares. And in our optical database of all these low mass extrabinaries that we have now, we are trying to see if we can find more sources for which we can see the color magnitude diagram and other diagnostic tools to say for sure that this is actually just the temperature in the disk, and actually the disk instability model is our best bet for understanding how these outbursts are starting. At the end of my talk, I have 3 take-home messages for you. Firstly, optical monitoring of black hole extrabinaries combined with multi-wavelength observations can be a very effective way to study accretion processes during quiescence in compact objects. Secondly, Swift J1910 is a very interesting source showing some peculiar behavior like clockwise rotation in the hardness intensity diagram. And I know that people working in extrabinaries, you would later find more sources for which maybe we have such kind of loops or such kind of behavior. Then I hope that you remember 1910, because I think once we have a lot of sources, we can try to understand what is causing this kind of behavior. And finally, Swift J1910 shows highly unusual and high amplitude repeated optical flaring, which is probably caused by the changing temperature in the X-ray irradiated accretion disk following the model of a single temperature black body continuously heating up and cooling. The results that I have shown here are presented in 2 papers. Both of them should be in archive by now. And I'm happy to take your questions now. And this is my contact email ID in case you have questions later too. Thank you.
Thank you so much. Okay, any questions? No, I cannot see. Yeah.
Do you have any models for what launches these heating and cooling waves to provide your, as you've indicated here on this slide? What's the physics behind that? I mean, this is not obvious that the disk is going to undergo repeated heating and cooling in the long periods of quiescence.
Yeah, so you're asking if we have tried to model these reflares to see if this is just the heating or cooling, because we cannot say it properly through the CMD only. Am I right?
Open question.
Hello, sorry, can you hear me?
Yeah.
I don't think she can.
So did you hear the question before?
Sorry, are you asking
Yes,
if
so
I can?
Yeah, the
Yeah,
question
can
was
you-
the physical origin about the heating and cooling waves in the disk.
So for now, what we think is that, although we have not modeled it, but what we think is that it is just a kind of a heating wavefront, which is started by some kind of a disk instability at one radius of the accretion disk, which is causing, and as the matter is coming closer to the black hole, we see that there is an increase in the brightness. And the only thing that we have right now is the color magnitude diagram and the black body model, which is a very simple model right now. But we can see how the temperature is increasing as the reflares are progressing. Now we are in contact with some people who have done modeling of, like theoretical modeling of disk instability model before for white dwarfs, to see if we can actually replicate this kind of reflares. But this was a completely observational paper, and we have not done any modeling till now. But this is in the plan for next paper or next project.
Other questions from here? No? Okay, so let's thank both our speakers. Thank you.